Have you ever wondered how much that road trip is really costing you? Imagine cruising down the highway, but suddenly you hit a toll booth that charge you based on the digits in your license plate. Sounds crazy, right? Today we are diving into a fascinating challenge where we'll uncover the secrets of toll cost. And I promise by the end you'll never look at your car's number the same way again. Alright, let's dive into solving this problem step by step. Just like we are brainstorming at a whiteboard together, our goal is to compute how many shortest paths there are to each digit from the toll cost of roads connecting various junctions. So let's break it down. First off, we need to define our graph structures. In our case, the graph will represent junction as nodes and roads as edges. We'll store this information in the way that allows us to easily traverse it later. We'll use a list of tuples where each tuple holds a distance, node, and the cost of the road. This structure is efficient for our needs because it allows for quick updates and lookups as we build our graphs. Next, we move on to the main method where the magic begins. Here we read the input, which consists of the number of junctions and the number of roads. This is our starting point. Understanding how many nodes we have is crucial for setting up our graph. Once we have that, we initialize our graph, creating a list for each junction to hold its connection. Now comes the fun part, building the graph. For every road given in the input, we add an entry for both directions. Since these roads are bidirectional, this means if you can travel from junction A to junction B, you can also travel from junction B to back to junction A. So we are creating a two-way connection in our graph representation. With our graph constructed, we need to initialize the result array. This array will keep track of how many shortest path ends with each digit from 0 to 9. Why this is important? Because at the end of our processing, we want to know how many paths cost correspond to each last digit. Now let's get into the heart of the algorithm, performing a breadth first search or BFS for each junction. BFS is perfect because here it explores all neighbors at the present depth prior to moving on to nodes at the next depth level. This ensures we find the shortest path to each junction efficiently. For each junction, we first set up a distance array, marking all distances as unvisited, that is -1. Then we initialize our BFS queue starting with the current junction. And as we process each junction, we look at its neighbor and update their distances if they haven't been visited yet. If we find a shorter path, we enqueue that neighbor to explore it further. Here's the key insight. After completing the BFS for a starting junction, we update our result array based on the last digit of each reachable junction distance from the starting point. This is where we tally how many paths leads to cost that ends with each digit. Finally, after processing all junctions, we simply output the counts for each digit from 0 to 9. This gives us a clear picture of how many shortest paths can be associated with each last digit. And that's the blueprint. By breaking the problem down into manageable steps, defining our graph, reading the input, building it, performing BFS, and finally tallying our result, we create a structured approach that's both efficient and easy to follow. And that's a wrap up. Our deep dive into solving the toll cost digit problem. We started by constructing a graph, the representation of the junction and roads using a list of tuples to store the connections and their cost. Then we implemented a BFS breadth first search algorithm to explore all possible paths for each junction, ensuring we captured the shortest path effectively. Finally, we tailed up how many times for each last digit of the total cost appeared, which is crucial for understanding the toll distribution. Remember, the key takeaway here are the importance of graph structures in handling complex relationships and the power of BFS in finding the shortest path. The combination allows us to solve real world problems like toll calculations effectively. Make sure to check out the source code link in the description below. And if you have found this content helpful, don't forget to subscribe for more coding challenges and hit that notification bell so you never miss an update. In our next episode, we'll be tackling more into advanced graph algorithms, diving into concepts like Dijkstra and A-star for optimal path finding. Trust me, you won't want to miss it. Thanks for watching and keep